Okay, so these are the electromagnetic radiation notes. One of the things that we would have noticed from the electromagnetic radiation exploration, or what is light exploration that you did yesterday, is that really light and electromagnetic radiation all comes from interactions or emission from atoms. And the reason that it comes from atoms is really because atoms contain charged particles. So they contain protons and electrons that then have an electric field, which then can create this electromagnetic wave because the electric field changes, and there you get the emission of light. So I'll just continue reading this. It says, light can be modeled as a particle where each particle of light has a specific energy that correlates to the change in the energy for the charged particle. Light particles are known as photons. And so one example of how a photon is generated, or the emission of light, comes from an atom. One way to show this is that in an atom we have the electrons on the outside of the atom, and we draw lines just to represent the various energy levels that could exist, and those energy levels are labeled with the variable n, and then it's basically whatever the n is equal to, that's the energy level for the electron on the outside of the atom. So the nucleus is down here. This is where your protons are and the neutrons, but the protons are the charged particles. And when an electron is excited to a higher energy level, and that can come from something like heat. So if you think about the fusion that's occurring in the sun, there's a lot of energy that's released in the form of heat from that fusion, and so that will excite the electrons in the hydrogen and helium atoms that are in the sun, and so then you have electrons at higher energy levels, and when they spontaneously relax to lower energy levels, because that electron is attracted to the nucleus through the electrostatic attraction between the electron and the protons, it'll spontaneously relax back down to those lower energy levels. When that happens, the electron has not only changed its kinetic energy, but also its potential energy. And so this accelerating charge disturbs the electric field because the electron has an electric field, and that disturbance then causes that electric field to be disturbed, and then it propagates through space. And so this is kind of the little symbol that we use for a photon, which is just basically one particle of light. As I've said, this is basically taking electric potential energy and converting it into light energy. That's the conservation of energy that's occurring there. Light can also be modeled as a wave. We know that light has wave-like behavior because actually there's a famous experiment called the double slit experiment where, similar to when you had two speakers in the sound wave lab that are separated by a specific distance, and then we get this interference pattern. I'm going to draw that right here real quick. So if you have like a speaker here and a speaker here, and they're emitting sound waves because they're disturbing the air around it, those waves then propagate outwards, and what happens is that there's an overlap point where these waves are combining constructively, and also points where they're combining destructively. And so this interference pattern of sound waves is also seen with light waves. If this is actually a screen that has two very small slits in it where you can let light through, if you're shining light on the left side here, you'll observe that indeed on the other side, if you have like a detection screen, you see that there's a pattern of some areas where, right in the center, where the waves are combining constructively, and you get maximum kind of detection of light there, and then areas where there's no you see no light because it's a destructive combination, and then you get that pattern kind of going upwards. So when we see this same wave-like behavior from light as we do with speakers. And then in the wave model for light, an accelerating charge creates this disturbance in its electric field the disturbance in the electric field propagates through space. It transmits energy away from the accelerating charge at a specific speed. So I'm not sure if we have a good theory as scientists for why all light or all electromagnetic radiation travels at the exact same speed in a vacuum. I will note that that's in a vacuum. But that this is something that we observe as scientists. So we call this speed of light by the variable c. And remember that light is the same thing as all electromagnetic radiation, and that's equal to 2.998 times 10 to the 8th meters per second. Often rounded to 3.0 meters per, or times 10 to the 8th meters per second. So all electromagnetic radiation travels at that speed in a vacuum. So the reason that we have this electric field propagation and magnetic field is because those two things are always linked through electromagnetic radiation. The changing electric field here induces a changing magnetic field as well. So that's why it's really the oscillation of both through space. So when an electromagnetic wave is traveling through matter, it interacts with it because matter is made up of protons and electrons. This electric field is able to interact then with those charged particles because they have an electric field. So when it's traveling through air or anything that contains matter, then the speed of light is actually slower often than when it's in a vacuum due to that interaction. And so the index of refraction are these values here given by an n. And so when you're in a vacuum, n is just 1. But if you're traveling through, like trying to put, when you shine light through salt or shine light through air or shine light through water, these are considered the index of refraction. So then V represents the velocity of the light waves is then equal to c, the speed of light in the vacuum, divided by n, which is that index of refraction. And then just like mechanical waves, the speed, v, wavelength, lambda, and frequency of a wave are all related through this equation, that the speed of the wave is equal to the wavelength of the wave multiplied by the frequency of the wave. So that equation holds for both mechanical waves and electromagnetic waves. The key difference between mechanical waves and electromagnetic waves is, of course, that mechanical waves require that there's some type of medium, so you need to have air in order for sound to propagate, for instance. However, electromagnetic waves, light will travel through empty space. So you've probably seen this nice spectrum before. This is the full electromagnetic radiation spectrum. And these waves interact with all types of matter, and really the way that they interact with matter is very dependent on kind of the size of the disturbance to the electric field that's propagating. So on the low end of this spectrum down here, this is where we have radio waves. Radio waves are used through communication devices like antennas and things. And so down here, this is the really low energy side of the spectrum. You'll also notice that the wavelength here is really long. So this is a long wavelength. And then you'll notice that if the wavelength is long, that means that the frequency is very low. So we have just 10 to the 4th here compared to 10 to the 20th. So I'm going to say small frequency. And some of this is connecting that, remember that all of them are moving at the speed of light, v, and then that's connected to the wavelength times the frequency. So if we have a large wavelength here, it means that we have to have a small frequency of those waves to have the same speed. And then on the other end over here, this is, of course, the high energy side of the spectrum. And so these have a short wavelength. You can see that here, and they must have then a very high frequency. So same speed, but the wavelength is very short, which means they have to have a high frequency. And then, so microwaves down here, microwaves, you know about like a microwave oven. Microwaves are oscillations in the electric field such that actually cause rotations to molecules. So this region right here often causes molecules to rotate. Also is emitted when a molecule will rotate. And so that's actually what's happening in a microwave, is that it's often tuned to the rotation frequency of water molecules, and so anything that contains water then will heat up, because as those molecules rotate, there's a lot of friction that produces heat and heats up your food. And then in the infrared region here, this is often what we associate with things that are warm, so infrared. An infrared camera can see things that are emitting infrared radiation, which comes from, objects that are warm. And in terms of what's happening to a molecule when infrared light interacts with it, is that it often causes molecules to vibrate. So those vibrations are due to an infrared wave interacting with it, or when they change their vibrational energy, they emit infrared light. Visible, we saw with the hydrogen atom that visible and actually into the ultraviolet, those are related to electronic changes in energy. So when you're actually moving an electron further away from the nucleus or bringing it closer. So electronic changes in energy. And then X-ray, those also can be electronic energy changes, but it's like often an electron that's really, really close to the nucleus and going really far away from the nucleus. So I guess this actually extends to here. And then the nuclear range is really the gamma rays. You might remember gamma rays from in your chemistry class when you studied nuclear chemistry, that gamma rays are often emitted when a nucleus undergoes some type of either beta or alpha decay. And so these are associated with, oh, that's a bad little bracket, nuclear energy changes. And you'll notice that it's not a coincidence that the size, the wavelength of a gamma ray is about on the size of an atomic nuclei, because, if it's just a radio wave, that radio wave is so long, it's on the size of buildings, that it has no influence on the nucleus here. And so the wavelength of the electromagnetic radiation, in order to interact with an object, it has to be around the same size as that object that it's interacting with. And then the region that we know the most here is really the visible spectrum, because that's the area of this electromagnetic radiation spectrum that we can actually detect as humans. So our eyes can detect from down to about 750, sometimes into 800 nanometers in terms of a wavelength of light. And then on the higher end of energy, or the shorter wavelengths, somewhere into 400, maybe 380. And so one of the things you'll come across in future science classes, chemistry or physics, is that they often ask you to kind of memorize what are the wavelengths for the different colors of light. But that's not something I'm going to ask you to do, but you can see them here. All right, and then the last bit here is about the energy of electromagnetic radiation. So the energy of a single photon is really directly related to the frequency of it. So on the high energy side here, the higher the energy, the higher the frequency, the higher the energy of that photon. And so this is given as E is equal to H. H is known as Planck's constant. Right here it's given, and then the frequency times the frequency. Or another way to write this would be that the energy is equal to H times the speed at which it's traveling divided by its wavelength. All right, and this part comes from the fact that if I take the velocity equation, I've got velocity is wavelength times frequency, and I rearrange this for f. I'm going to divide by wavelength, and I get that f is equal to v over lambda. So in this equation, I've just substituted v over lambda for frequency. So just two ways to calculate the same thing. So if you were asked to figure out like how much energy is in a single photon of violet light, you would be able to determine that by then plugging in Planck's constant here, the speed of light, assuming it's in a vacuum, so 3.0 times 10 to the 8th meters per second, and then divide by the wavelength here, although you would need to convert the nanometers here into meters. And so this is where you often need those conversions in the metric system. I'll just write it here that as a reminder that 1 meter is equal to 10 to the negative 9th nanometers. So you could use that conversion there. All right, and that's it for electromagnetic radiation in the full spectrum.